Hey guys. So today we're just going to do a really quick lesson on standard form. Now, standard form is extremely important because we're building our ability to be able to use the simplex method. And to use the simplex method, we need things to be in standard form. We absolutely need standard form. Now, this gives us all the nice structure that we need in our problems to be able to find extreme points through the simplex method. Now, the question is, what is standard form? Well, it's quite simple. All of our constraints need to be written as equations. Now, this is a little different from what we've been writing because we've been writing, computer lagged, all of our constraints as inequalities. So we need to figure out how to fix this. Okay, and that's mainly what we're focused on in today's lesson. The other piece we need is we need all our variables to be non-negative. Well, lucky for us, so far we've been writing all of our variables with non-negativity constraints because they've naturally had them. Everything in life doesn't naturally have this, so we may need to fix this later in the semester, but for right now, we kind of have we're at a happy spot here, okay? Now, we'll pay attention to non-negativity because when we fix our inequalities and turn them into equations, we need to keep this non-negativity in mind. And there's kind of one that a lot of textbooks leave out, but it's because we're studying LPs. I just put ... It's that we need things to be LPs. This only works if we're doing linear programming. Obviously, we want our constraints and our objective function to be linear. I find linear is nice, but that's what we need. Otherwise, none of this stuff works. Okay, so we don't have to worry about this because all I'm going to give you are linear programs. Later in the semester, we'll look at things that are not linear. Okay, so let's mosey on. Let's just jump into our first example. So this is an LP. We're maximizing some objective function subject to these constraints. And notice both of them are less than or equal to constraints. Okay, so we have an LP. We have two constraints. They're not equations yet, they're inequalities. And we have non-negative variables. So we're almost there. So mostly what we're going to end up fixing after we model a problem are these constraints. We need to make them equal signs. Well, how do we fix them? Let's look at the first one. I'm going to just leave some space and put 40, okay? So we're trying to equivalently get an x1 and x2 value that are less than or equal to 40, okay? Well, it's really simple if x1 and x2 equal 40, right? Boom. But that's not going to be the case over all the points of our LP. We need to represent the entire feasibility region, that these can be less than 40 as well. But we still want this equal sign here. So how can I do this equivalently? How can I get these two things, these two expressions, to be equivalent? Well, the idea here is I can introduce a new variable, kind of a dummy variable. What they call them are slack variables. Some textbooks call them slack or excess, depending on whether we're adding or subtracting them. So think about this. If x1 and x2 do equal 40, and I have this slack variable here, I'm just going to use s for slack. x1 and x2 do equal 40, this slack variable would be equal to 0, and so we're able to capture that easily. Now, if x1 and x2 are less than 40, we could just add some value to the slack and to push it until it's equal to 40. So then this x1 and x2 can take on all the same values that they took on over here, because we know they can't go into the negative, so they can go as low as 0, and they can go as high as adding to 40. Which is what these x's can do. I put this slack here to just pick up any slack to make sure we are equal to 40 in the constraint. x1 and x2 can still hold all the same values. Okay, so rewriting the entire LP, honestly, I don't have to rewrite the objective function, but I will. The slack variables are nowhere in the objective function. So that's really nice. They don't add anything to the optimization problem. They just help get us this equation structure. So they're really intelligent. And so let's look at the next one, 2x1 plus x2. It's less than or equal to 60. We can fix this in the same way. Now, I don't want to just add the same slack variable, because if this is slacked by 20, this one doesn't necessarily have to be slacked by 20. So what I'm going to do is give each constraint, whoops, that's a 2, its own slack variable. Okay? And now non-negativity, x1, x2. But I just introduced these two variables. They have to be non-negative as well. So there. That fixes everything. I need the non-negativity here because the lowest x1 plus x2 can be is 0. If this were negative, then though, x1 and x2 could be, well, this whole thing could be less than 40, but I guess it wouldn't be if we have equals 40. The problem occurs when x1 and x2 can't be bigger than 40 over here, but if this could be negative, then I could let this be like 100 and this be 100 and this just be like negative 160 to push us back down. So this has got to be positive or non-negative. And so there we have our constraints. We have our standard form LP. All we did was add slack variables. So a general rule of thumb is, as long as everything's kind of like all the problems we've been looking at in this class, if you have the constraints as less than or equal to, so let's call this the left-hand side as less than or equal to some number, we're just going to take that left-hand side and add a slack variable to be able to say it's equal to that. Okay? It's a very simple but very, very intelligent idea to handle this converting to standard form idea where we want equations. You'll see next lesson why we want equations. Actually, you'll see kind of throughout the next few lessons why we want equations. Alright, so that's how you fix less than or equal to. Well, I think then you're pretty good to understand really easily how we're going to fix greater than or equal to's. So let's just take the first constraint and look at it. So 2x1 minus x2, we would like for it to be equivalent to 2x1 minus x2 is greater than or equal to 10. So think about this. These variables can take on any values as long as they're 10 or bigger. So obviously they can subtract to 10 or combine to give you a value of 10. But they could be bigger than 10. If I want to say this is equal, say this is say these two, say this is 6 and 0. That would be 12 minus 0 is 12. So what I'm going to want to do to get down to 10 is subtract off a slack variable. Okay? So then these x's can take on any value 10 if the slack is 0 or greater, and then the slack will pull us down to 10. And this is a greater than or equal to as well, so I can easily write these constraints. Adding, once again, each constraint will get its own slack variable. And then, of course, everything's got to be non-negative. I'm not going to waste time rewriting the objective function and rewriting those, but I guess I'll rewrite these. The x's have to be non-negative, and these slacks that we introduced have to be non-negative as well. So here, just pretend you plopped that there. So as a general rule of thumb, if you take the left-hand side of a constraint and it's greater than or equal to some number, what we're going to do is we're going to take that left-hand side and subtract off a slack variable so that we can say it's equal to that b, that number. Okay. Now one last example, because people get confused. They think they're always going to do the same thing inside an LP, but we can have less than or equal to's and greater than or equal to constraints. We can just combine this idea really easily. So if we just combine this idea, I wanted to write this in standard form, we would just need to, here, I won't be lazy this time, I'll actually write out the entire LP. And so take our objective function value, it doesn't change. Then we go to the constraints here, and let's look at the first constraint. It's a less than or equal to. So that means that I'm going to need to add a slack variable so that I can say that's equal to 10. Let's look at the second constraint. It is a greater than or equal to 8. So what I'm going to need to do is, if these are over 8, I need to subtract some slack off S2, so I can say it's equal to 8. And then, of course, my slacks have got to be non-negative. Okay, so then we have put this thing in standard form. Standard form is extremely valuable to us. Okay, and it's basically why the simplex method works, or not why, but it gives us the structure we need for it to work. Alright, so it's not hard. It's actually super simple to understand how to do this, but it's extremely useful. Alright, well, that's all I have on standard form. So next lesson we'll look at just looking at these constraints that we have now turned into equations. How can we use them in an interesting way? Alright, have a good day.